Hello, calculus. Hope everybody's having a fantastic day today. Today is number 2 of the fundamental theorem of calculus. Let's jump right into it. This is just another theorem. Remember that when you're working with theorems, they sound a lot more complicated than they are, and you'll kind of see that when we start doing some examples down here. What this is saying is that this function that we're given, it says if f and g are continuous, you got two functions, f and g, on a to b, then the function capital F of x is the integral of f of t from a to g of x. And it has a derivative at every point, and the derivative of capital F is f of g of x times g prime of x. Now here's a point that I want to drive home really quickly. We're going to call this fundamental theorem of calculus part 2, so number 2, and that's this right here. We are going to use the fundamental theorem of calculus number 2 when the top bound is a function. And the bottom bound is a constant. So if it goes from a number, your integration goes from a number to a function, then you're going to use this theorem right here. So here's an example of what this will look like, and I think it'll make a lot more sense once you get into this. First, for the integral of a to g of x, you know that what we are doing here is trying to figure out what we're trying to do is figure out the integral by plugging in g of x, right, f of b, and then plugging in a, which is f of a. So let's kind of go through and check this out. To start off with, it says find capital F prime. Now this is going to be a real key indicator to use my fundamental theorem of calculus part 2, because I'm basically finding the derivative of the integral. This should be fun. So find the derivative of the integral. I'm going to use this information right here, and what I'm going to do is plug g of x into f. So what I'm going to do to start this thing off, capital F prime of x, I'm going to take this x squared and plug it in where I have t. Alright? That's how I'm going to start this thing off. I'm going to take 1 over, this is this part right here, take g of x and plug it in, 1 plus the square root of 1 minus x squared. Here's my g of x, which is x squared, times the derivative of g of x. Well, what's the derivative of x squared? It's 2x. F prime of x. And then simplify. 2x over 1 plus the square root of 1 minus x squared. And that's really all there is to it. I just have to follow this formula. Plug in g of x wherever you have a t, right? It can be any other variable too. If this was u du, then you would plug it in for u, times the derivative of g. So it's almost like a chain rule, but a little bit different. A little bit different there. Let's do number 2 here. Zoom in so you can see it a little bit better. Number 2 says f of x is the integral from 0 to x cubed of sine of t squared dt. Now keep in mind, you are trying to find the derivative of an integral. So it should make sense that if you're trying to find the derivative and you have an integral sign, that they're going to cancel out. A derivative and an integral cancel each other, right? It's like putting polar opposites next to each other. They're going to go and stuff happens. So just follow the format. It's first we plug in x cubed into t. So it's sine of x cubed squared times the derivative of g of x times 3x squared. And then simplify. 3x squared sine of x to the fifth? Sixth, excuse me, I'm sorry, we're multiplying here. Raising an exponent to an exponent, we multiply to the sixth. Excuse that. That's really all there is to it. We just plug in this expression and then multiply it by the derivative of that. And that's all there is to it. All right, number 3. Now number 3, the first thing I'm going to look at again, and I'm sorry, I looked at it up here, but I didn't point it out. The first thing we looked at to make sure of was that we were integrating from a number to a function. Down on number 2, we were integrating from a number to a function. That means we can use the fundamental theorem of calculus, number 2. But on number 3, for example, I'm integrating from a function to a function. I've got a variable down here. So I'm going to put a little note over here to the side that says do not use FTC number 2 because lower bound is not a constant. I misspelled constant. That's okay. Constant. Do not use the fundamental theorem number 2 because the lower bound is a constant. So you're like, well, what do I do then? I'm going to work this just as I normally would. I'm going to work it just like normal. I'm going to take the integral of 2t. What is that? The integral of 2t is t squared, isn't it? And I'm going to evaluate that from x to x plus 1. So I'm literally doing exactly what I have right here. The fundamental theorem of calculus number 2, what we did in the previous 2 problems, is a shortcut. And now you can kind of see where that's coming from, right? And up here, I could jump from this f of x to f prime and just plug in information. See, now what I'm going to have to do is f of b, right? So this is x plus 1 squared, that's f of b, minus f of a, x squared. And I'm going to have to come up with what f of x is first. Let's simplify this and figure out that f of x, capital F of x here, x plus 1 squared is x squared plus 2x plus 1, and then minus x squared. So capital F of x is, these two will go away, 2x plus 1, right? Okay, and then from here, I would have to take the derivative because the directions are the same. The directions are to find f prime of x, capital F prime of x. So what I did is figured out what f was by just doing this straight out. Figure out what f prime is by figuring out what that is and then taking the derivative. And the derivative happens to be 2x plus 1. The derivative of that is 2. Right? Now, I want to put this over here to the side. What if there was a different way to do number 3 here? We could say or, right? F prime of x, I can jump to what f prime of x would be, and both ways would work pretty much the same. You know what? I'm not going to do that. Just for the sake of, I don't want to confuse anyone. I can already see the stairs. Don't look at me that way. I see the stairs. Don't look at me that way. I don't want to confuse anyone more than that. So I'm just going to leave it at that. That seems like a pretty easy idea, right? Instead of using numbers, use equations. Plug it in. But if it's a constant on bottom and an equation on top, the fundamental theorem of calculus number 2 is a shortcut. And shortcuts are amazing. Number 4. All right, this is awesome here. This is a visual look at what FTC number 2 does. So it says the graph below represents a differentiable function f. See this guy right here? That's what's graphed. On the closed interval 0 to 7, shown below. And it says let h of x be the integral of f of t from 0 to x. See how we're integrating f right here? Alright, so let me just clarify. This is f of t. This is our function f, right? And it says h is the integral of f. So let me write this out here. This is what each piece is going to mean. The integral of f is the area under f, right? So h of x is the area under the curve. Right? Area under the curve. The curve itself is f of t, right? And that's just kind of a side note, so I'm going to put this over here. F of t, I'm going to put this over here on the side, is the curve itself, right? So h is the area under the curve. Well, what would h prime be? In other words, if I took the derivative of the integral, right, plug in an x, excuse me. If you take the derivative of the integral, shouldn't I end up with f of x? If I take the derivative of the integral, I should end up with f of x. So if h is defined as an integral, the derivative of that, plugging an x in for t, will give me f of x. And this guy came from the front page. This is the fundamental theorem of calculus number 2. It says that the derivative of h of x, which is defined as an integral, so the derivative of an integral is the function. Well, that kind of makes sense, right? If you started a function and integrate it, you're up here, take the derivative, now you're back down here as far as powers go. That just kind of makes sense. So what would h double prime of x be? Well, that would be the derivative of the function, wouldn't it? Let's use that information and find out something cool here. A says find h of 2, h prime of 2, and h double prime of 2. Well, we said h of 2 is the area, right? So I'm going to find h of 2. That's this guy up here. That's the integral from 0 to 2 of f of t dt. So I need an area from 0 to 2. So I have an area, looks like right here. I'm looking for this guy, this area and this area. So it looks like 2 triangles. So this is going back because I don't have an equation to use. I got to go back and use my graph up here. So two triangles is what it looks like. 1/2 base times height. So 1/2 my base is 1. My height on the first one is 4, looks like. Plus this area, my 1/2 base times 1, or base is 1, my height is 3. Which is 4 over 2 plus 3 over 2. 7/2. That's h of 2. What about h prime of 2? Well, we just said up here that h prime is f, right? So what they're really wanting to know is, what is f of 2? So go to your function, put a 2 in. Here's 2. Find my function. It equals 3. Oh, this is fun. H double prime of 2 is the derivative at 2. Oh, now we're getting interesting. See, here's 2. What's the derivative of the function right here? Well, that's a cusp, isn't it? That looks like a pretty sharp turn to me. That's going to be undefined. All right. Or you could say it does not exist. Right? The derivative does not exist there. We might want to stay away from the word undefined because technically that means you're dividing by 0. So let me state it as does not exist. I think that's a little bit more succinct. And then, oh Lord, write an equation of a tangent line to x? What? Okay, I know I see equation of tangent line. Well, we all know that a tangent line means I need a slope and a point, right? at x equals 2. Well, how do you find the slope, or how do you find the slope at x equals 2? You would have to do h prime of 2, right? H prime of 2, which is, whoa, we already figured that out. That's 3. Oh my gosh. And then if you plug in 2, your point is going to be 2 comma h of 2, right? Plugging a 2 into x. What? We already figured that out too. 7 halves. That's 2 comma 7 halves. Oh, this thing is building itself. Y minus y1 equals m times x minus x1. Calculus. You've done it again. And then C says, what is the domain of H? The domain of H. Now, H is the area under my curve, right? What's the area under my curve? See, what I'm going to have to do is go back and look at my graph up here. And I know I'm going somewhere between 0 and 7, right? If you count this out, this is 1, 2, 3, 4, 5, 6, 7. The question is, do I have some form of area between those numbers? Well, yeah. My domain is 0 to 7. If my function is only and you can write this way, or you could say 0, 7. If my function is only defined from 0 to 7, my derivative is, or excuse me, my antiderivative is not going to magically change domains. Now, it can change domains if I put a restriction on it, but there's no restrictions here. A restriction would say integrate it from a certain point to a certain point, kind of like number A, or letter A right here, 0 to 2. Well, that would restrict my domain, sure. But it says, what's the domain of H overall? The whole picture of H comes from the area under this curve, and the curve is defined from 0 to 7, so there's my domain. Peace!